Hello? Great. Hello, everybody. Can you hear me? Great. I am so excited to welcome you to University of Washington's inaugural Physics Slam. So I am CUWiP. I am a professor in the physics department and the electrical engineering department, and I have my undergraduate degree in physics, and my research is in quantum information processing. I am so excited about this event, and we're going to learn more about what exactly this event is shortly from the people presenting the event. But before we start, I wanted to take a little bit of time to tell you about another event that's going on this weekend. As some of the general public audience members may have noticed, the audience today does not look like a typical audience for a physics lecture. Something is different. The University of Washington is extremely proud this weekend to be hosting our region's APS conference for undergraduate women in physics, also known as CUWiP. About 185 women have descended upon us this weekend. About half of them are joining us at the conference, because one thing we didn't anticipate was that when we filled their whole day with physics, we didn't leave any time for them to do their problem sets. So some of them have left us tonight to go work on the homework that is still going on during their term. Okay, so the goal of the conference, so we have about half of them, so let's give a round of applause for the people that are really stuck it out. Woo. They have essentially been doing physics since 8:30 this morning. All right. So one of the goals of CUWiP is that one day, audience makeups like this one will no longer be an anomaly. All right. As people interested in physics, we often get a raised eyebrow. Why physics? Everyone's answer is different, but for many people, there are two general sentiments. First, knowledge of physics allows us to change the world. As an illustration, because of our understanding of physics, we can control the conductivity of a material by 10 orders of magnitude, enabling all the fun features of the devices in your pocket right now that are hopefully on silent. There are so many more examples. Energy-efficient lighting, enabled by the discovery of the blue LED, and magnetic resonance imaging are two such examples. And if we think or reflect, we can realize that the technological problems physics will tackle in the future and the fundamental phenomenon that we as a people choose to explore is determined by who is a physicist. To the young women who are joining us tonight, physics needs you. All right, so why physics? A second common reason is that the knowledge of physics allows the world to change us. I teach 121 sometimes, the introduction to physics, and I had a student came in. He was very frustrated. He was not doing well in the class. And he said, I don't understand. Since I started taking your class, I can't do anything without thinking about physics. I go to the gym. I can't even go to the gym. All I can think of is torque and lever arm now. And I sat there and I said, I know this is not much consolation because you're not getting a good grade in the class, but you've just told me something that is what I'm actually trying to change about you as a student. So be patient. You're getting there. And I didn't have the heart to tell him that it just gets worse. Whether you're watching a leaf floating from a tree like a helicopter, looking at a clean stream enter a dirty river, holding a coffee cup and feeling your hand get warm, or looking through a double-pane window that is fogging up. It's like a new set of eyes, a sixth sense, and no one should be deprived of the opportunity to understand how our universe works. The importance of the Conference for Undergraduate Women in Physics is recognized by APS, the American Physical Society, and the Department of Energy, DOE. These government organizations are the primary sponsors of this conference, so let's give them a round of applause. The value of CUWiP has been recognized by many of our own Pacific Northwest companies. 8 of them has sponsors this year's CUWiP. Yay. The particular sponsor for tonight's event is Global Good, funded by Bill Gates and focused on a shared vision with Nathan Myhrvold. Global Good invents technology to solve some of humanity's more daunting challenges. I asked Global Good how they would like us to recognize their sponsorship tonight, and I love the simple answer I received. Overall, this is what they said. Overall, we would like to signal that we are expanding physics in our lab, and we are very interested in attracting women researchers. They and many other companies are recognizing the need to have a diverse workforce trained in physics. Now on to the slam. I would like to introduce tonight's MCs. Bryn McCoy. She's a UW graduate student in physics, measuring the anomalous precession frequency of a muon in a toroidal electromagnetic storage ring. Otherwise known as studying particles acting like spinning tops. Meredith Foray is a UW graduate student in physics, studying the quantum mechanics of molecules with large amplitude and harmonic vibrations. Or, again, for the layman, floppy molecules. So I'm going to hand the mic over to our MCs now. Thank you.
Thanks, Kaimei, for that introduction. Hello, and welcome to the Physics Slam. As she said, I'm Meredith.
And I'm Bryn, and tonight we are going to be your guides through the wonderful world of physics.
5 physicists will be competing to tell you about their research in no more than 10 minutes. And then at the end, we'll have a few minutes for you to ask them questions about their presentations.
And then you will vote for a winner online. So please have your phone or your internet-enabled device ready to do that. Also, the winner gets the satisfaction of a job well done, but also they get this awesome stainless steel mug with an electric mug warmer.
Okay. So let's get right to it. Our first contestant is Dr. Megan Ivory. In West Pennsylvania, born and raised, now in the laser lab is where she spends most of her days, chilling and trapping ions so cool, making a quantum computer at UW's physics school. Here's Megan Ivory from UW's Trapped Ion Quantum Computing Group.
Hi, everybody. Can you hear me? The light is on. Can you hear me? Great. Okay. I need a clicker. I got excited. Here's your clicker. Thanks. Hey, all right. Is everybody ready to learn some physics? That was a great response, but I'm actually going to start off talking about art. So art, in its simplest form, is just a way of modeling the world around us. So wouldn't it be weird if all of the world's greatest art could only be made with black and white? You could kind of get a picture of what's going on, but if you really want an authentic replication of the world, you have to have color. Which is what brings me to physics. Physics is just another way of modeling the world around us. But instead of using canvas and paints and brushes, we use a lot of equations and oftentimes computers. So what if I told you that until recently, our most powerful computing tools were only modeling our world in 2 colors? When in reality, we know that our world is color. So we have to have quantum mechanics. That's the color in this analogy. Okay. So quantum mechanics is what governs our world at the smallest scale, the atomic scale. It's what determines how atoms come together to form molecules that could be the next life-saving medicine or world-changing material. And it's really weird. In quantum mechanics, Particles can act like waves and interfere with one another from a distance, and waves can act like particles and are quantized. Furthermore, those classical bits of information, which were previously limited to 0 or 1, can now be 0 or 1 or both at the same time. So it's no wonder that when we try to model our quantum world with classical computers, we quickly reach the limit of what they're capable of. We need a better tool. We need quantum computing. So in quantum computing, our bits of information are simply called quantum bits or qubits. And our qubits can be any quantum mechanical system with discrete energy levels. So there are a lot of choices for qubits. I'm going to tell you about one particular one that we're studying right here at the University of Washington called trapped ion qubits. So for the rest of my talk, I'm going to explain our particular qubit of choice, barium-138, tell you how we trap it, and finally how we cool these ions in order to be able to use them for quantum computing. So barium-138. If you remember your periodic table, barium is in the second column, which means it has 2 valence electrons typically. And those valence electrons are orbiting around and hanging out. But at this point, I'm a very balanced atom. So I have 2 electrons, I have some protons floating around, and everything's cool. I don't want that. I want to be ionized. I want to get positive. So the first thing I need to do is get rid of one of these electrons. The way that we do that is we shine a really powerful laser on it, and one of those electrons absorbs so much energy that it's no longer confined by the nucleus. Okay, so now I'm positive, yay! All right, now that we have an ion, it's really easy to trap because ions are very sensitive to electric fields. So remember that like charges repel one another. So if you put me inside of a room with positive walls on 2 sides, I'm going to be repelled from those walls. So in this scenario, I'm going to try to get to a negative wall. If as I approach that wall, we quickly switch up the scenario, now I'm going to be going towards a negative wall on the other side. So if we switch this fast enough, I'll just kind of get jostled around in the middle. This is actually how we trap ions in our laboratory. And you might imagine that we do this with a very sophisticated scientific equipment. And we do, but you can also do it in your garage if you just have a high voltage oscillating source and something charged, like maybe some little styrofoam or charged dust particles, and some kind of electrode. So this is a video of just that. 5 tiny little ions, not single atom ions. And what is this scientific apparatus? It's a paperclip. You too can do this. All right, so once we've trapped our ions, we want to cool them down. All of this wiggling motion and jostling around is not very useful to us. So cooling down essentially means slowing down in physics. In order to do this, we use perhaps what is the coolest tool possible for cooling. We use lasers. And we call it laser cooling, which sounds so weird. But I'm going to tell you tonight how to do laser cooling. And you only need to remember 2 things in order to understand how laser cooling works. I'm going to explain them to you right now. The first thing you need to understand is the Doppler effect. So you've seen these signs. It's the same thing that when you're out on the street, the cars go by, they go, "Meow." Okay? So what's happening here is as a vehicle is approaching you, you can think of those sound waves as getting squished up and compressed. They're shifted to a higher frequency, or blue shifted, because higher frequency is more energetic, and so is blue. On the other side, as the vehicle is moving away from you, you can imagine those sound waves getting stretched out. And that means they'll have a lower frequency, and they're less energetic, so we call that red shifted. That's the first thing you need to know. Got it? Okay, second thing we need to know is about barium itself. This is barium's dating profile, I think. The only thing you need to take away from this is that it has a very particular favorite color. Blue, but not just blue, 493 nanometers. The reason that it likes that color is because of the energy structure of the atom itself. So typically, this electron is floating around in the ground state. But there's another state up there that the electron can jump to called the excited state. And the energy difference between the ground and the excited state happens to be 493 nanometers, which is right about there on the visible spectrum. So how does this work? If I am your ion, and I encounter my favorite color, blue, something's going to happen. What's going to happen? I'm going to get excited. You guys are right. And then my electron's going to be way out here. And after some period of time, I will re-emit a photon, send it back into the world, and go back into my ground state. Okay? Those are the two things you have to know. Are you ready to put it all together? Yeah. All right. So we've got our ion. Where's our ion? There's our ion. Our ion's moving around. Remember, we need to cool it so it has some motion to it. Let's say it's running in this direction. The next thing we're going to do is shine a laser on that ion. We're going to choose a very particular color, not its favorite color. We're going to choose something that is red detuned, so less energetic than its favorite color. And the reason is the Doppler effect, because as that atom is going in this direction and the laser is coming in this direction, I'm going to see that light as my favorite color. It's going to be blue shifted, which means it's going to be closer to resonance, my favorite color. I'm going to absorb it, but that photon also has momentum, and that momentum is going in the opposite direction of me. So when I absorb that momentum, I slow down. This is what we do in the laboratory when we cool our ions. It's very effective. Here's some numbers for you. You can go from hundreds of miles per hour to less than 1 in 0.01 seconds or less. That's crazy fast. So when we do this in a laboratory, it looks slightly different. We have a setup something like this, but when it all works, we have systems that can produce single ions right there, that tiny little dot. And I'll zoom in for you. It still just looks like a tiny little dot. So in my group here at the University of Washington, we are studying not only single ion quantum computing and other information, but we're also studying larger qubit groups, such as this one. These are 10 individual barium ions trapped. And when you add more than one, they will crystallize because they repel each other. So they want to be in the center of the trap, but they also don't want to be too close to their neighbors. So they form these very beautiful structures. Each of these ions is a qubit. And so each of those ions has a ground state and excited state, which we can call 0 and 1 in our qubits. And we can control whether it's in 0 or 1 or both using lasers. So that's all I have time for today. I just want to put up the names of my group members who have helped produce some of these beautiful images. And thank you so much.
Okay, let's thank Dr. Ivory again. That was amazing. Okay, our next contestant is Dr. Joey Shapiro-Key. We will welcome her in just a moment. Oh yeah, perfect, okay, good. Dr. Key is originally from Langley, Washington, on Whidbey Island. She's an assistant professor at of physics at the University of Washington, Bothell, and growing up, she wanted to be a wide receiver for the Seattle Seahawks. But she was never drafted. So instead, she became an astrophysicist, pretty typical, and plays ultimate frisbee. Let's welcome Dr. Key.
Thank you. Good evening It's great to talk to all of you tonight. Let me see if I can get that video to play one more time. Great. Okay, so from the very small to the very big. 100 years ago, Albert Einstein predicted that accelerating masses would create ripples in space and time that travel at the speed of light. We call these gravitational waves. They are created by very massive objects in our universe, such as black holes, orbiting around each other. When they collide, they create a lot of gravitational waves and collide to make a bigger black hole. So that's the animation that we just watched. And this animation was created to show what it would look like if we were close enough, but a safe distance away, to two black holes as they collided, making gravitational waves, the very first gravitational wave signal that was ever detected by humans. The experiment that made this detection is called LIGO, the Laser Interferometer Gravitational Wave Observatory. There's a detector in Livingston, Louisiana, and another detector in Hanford, Washington, just over the mountains. Has anyone ever been there? Everyone should go visit in the Tri-Cities area. You can visit LIGO. These are laser interferometers. We just learned a little bit about lasers. This is another great use for lasers. LIGO uses lasers, a laser in the central station there, and then a beam splitter that splits the laser into two parts and sends it down these long arms. They're 4 kilometers, about 2.5 miles long. They're long vacuum tubes, some of the largest vacuum systems in the world. Then there's mirrors at the end of those long arms that reflect the laser and bring it back to the central station to measure very, very precisely the length of the arms to tell if gravitational waves have passed through the instrument and Earth and us, changing the length of those arms by just a tiny bit. Einstein didn't think that it would be possible to detect gravitational waves. And indeed, it took 100 years of human ingenuity to build these instruments to make the very first detection of gravitational waves. And we can actually hear the gravitational waves in the LIGO data. It's called a chirp. You can sort of hear a little bit of the frequency sweeps up. You can also see it in the graph there. So that is what it sounds like when black holes collide. Maybe not what you were expecting. But it is actually what we calculate and predict for a black hole collision, and indeed what we heard on September 14th of 2015, which was the very first detection of gravitational waves. Then, in August of 2017, we got a new kind of signal. This one, which also sounds a little bit like a chirp, so you sort of recognize the sound, came from, instead of 2 black holes colliding, from 2 neutron stars colliding. Followed by, in this case, when 2 neutron stars collide, it turns out there's some messy astrophysics that happens, and there's a bunch of light that is also created. When black holes collide, it is still dark, but when neutron stars collide, it makes light. And so a NASA satellite called Fermi has a gamma ray burst monitor, and just after we detected the gravitational wave signal from 2 neutron stars colliding, the Fermi satellite detected a gamma ray burst. Gamma rays from a distant galaxy. This joint detection set off a worldwide search for the galaxy where those 2 neutron stars collided. Now, it turns out that gravitational wave detectors and gamma ray burst monitors are not very good at telling what direction the signal came from. But working together, the 2 LIGO detectors, a third gravitational wave detector in Italy called Virgo, and the gamma ray burst monitors on Fermi and Integral worked together to find the portion of sky where the signal came from. Then some telescopes in South America searched the sky, looked through all those galaxies, and found the host galaxy where there was a bright new star that we now call a kilonova from the 2 neutron stars colliding. So this is the first, what we call multi-messenger astronomy detection with gravitational waves and light. And this kilonova was studied by pretty much most of the astronomers on Earth, with telescopes on all 7 continents, and astronomers all over the world observing this kilonova event and the light and afterglow that came after the collision. So LIGO is now probing the population of black holes in our universe. There have now been 10 black hole collisions that have been observed by LIGO. You can see them up on the top here, as well as the neutron star collision at the bottom there. When those 2 neutron stars collided, you can see the little arrow points up to a little question mark. We're still actually not sure if after the neutron stars collided, if they collided to form a black hole or a neutron star. And we don't have enough data to be able to tell which one it was, so we hope to detect many more of these kinds of signals to be able to start answering these kinds of questions. And we all now live in the era of gravitational wave astronomy. This is a totally new kind of astronomy. We'll be exploring pairs of black holes. We don't know a lot about black holes out there in the universe, so this is a great way to do it. The LIGO detectors right now are being upgraded and will turn on for our 3rd observing run this spring. So keep an eye out for more detections coming up later this year. We really are lucky to be living in this time when there's a totally new way for astronomers and humans to be able to explore our universe. So thank you.
I can get it, yeah, thanks. Okay, let's thank Dr. Key. Our next contestant is Gray Rybka, Dr. Gray Rybka. Dr. Rybka is a professor of physics at the University of Washington. He studies dark matter and neutrino physics. He stole something out of the introductory physics demo storage for you today. So let's welcome Dr. Rybka.
Good evening. So I have to apologize. I made 3 big mistakes in coming here. I'm remedying them right now. So number 1 was obviously sound effects are key, but I did have a key to the demo lab, so I've got it's a bit lower fi, but I've got sound effects too. Mistake number 2. This is for a general audience. No technical terms. My title is The Search for Axion Dark Matter, and I've already violated that twice, so I have some explaining to do. But I can get to that. The third one I don't think I can remedy because it seems like the purpose of the speakers is to get you all in a position where you learn more about the universe. You step away from these knowing more about the universe, and I actually kind of want to make you learn to know less about the universe when I'm done. I can't really fix that. So sorry about that. Right, so yeah, I'm Gray Ribka. This is the ADMX, the Axion dark matter experiment that I work on. Let's start on the dark matter part first. So what do I mean by dark matter? Well, you and I, we're basically the same, right? I mean, from a physics perspective, you and I are the same, as we're the same as the chairs you're sitting on and the Earth, and we're pretty much the same. Oh, sorry, we're also pretty much the same as like the sun, other galaxies, all about the same stuff, right? We're all made out of atoms. So we're going to get along just fine. And we would be forgiven to think, okay, we've got this whole universe thing pretty well figured out. But there is some unfortunate messages from astronomy, and these messages come in at all scales, starting out at the scale of the entire universe. Yeah, I can't go into great detail about all these. If you look at the temperature of the sky, which is taking the temperature of the entire universe out there, you see bumps and lumps, and you compare these bumps and lumps to our understanding of how the universe formed, and you get that there's a lot of stuff out there that isn't made out of atoms, which is funny because we haven't really noticed things that weren't made out of atoms. So you look into a smaller scale, but still unimaginably huge, and that is of clusters of galaxies, and you can map out where the stuff is and where the stars are, and they're not in the same place. And where the star, and there's also, you could say, well, where is the gas, where's the dust? Well, it's not in where most of the stuff is, so there's some stuff out there that isn't stars, dust, gas, or anything else made out of atoms. Okay, let's look at a smaller scale. We can look at individual galaxies just like ours, and say, okay, so some of you have taken your early physics and you learned Kepler's laws, the planets moving around the sun, and you know how fast they ought to move given how far they are out, and you say, okay, a galaxy is a big clump of stars in the middle and then some stars off to the side, and I ought to know how fast they're moving. No, you don't. You got it wrong. Kepler's law is not working. But they do work if you go back and say, well, what if there's a whole lot of stuff out there that's not with the stars, that's kind of diffusely spread out? Since we suspect there's stuff in, there's the entire universe, there's clusters of galaxies. Well, now this stuff has gotten into your galaxy. So the next scale down, from my perspective, is you go straight from the galaxy into the laboratory, and that's where we, as of yet, have no evidence. And yet, since this stuff is in galaxies just like ours, there's every reason to believe that in this room with us right now, there is stuff not made of atoms. Don't look behind you, but it's probably behind you. It's under your chair. When you go home, when you try and go to sleep, it's under your bed. It's in your closet. So it's stuff we know absolutely nothing about. So you know less already. Oh, and there's a lot more of it than us. So all right. So you already know less about the universe than we started. I'm not even going to mention beyond dark energy, of which there's much more of, and it's even more mysterious. Okay, great. To which the enterprising physicist says, good, let's find it, bottle it, and sell it. To do that, you've got to have a guess about what it's made of, and for this, you've got to come up with some ideas of what the particle ought to be called. The one I like is called the axion. And I took this slide from one of the UW physicists, one of the UW theorists here, Ann Nelson, because I really liked it. The implication is that there's a whole lot of theories for different dark matter out there, and she was making the argument that if you want your theory to be natural and elegant, for whatever that means, you really ought to pick a theory with dark matter axions. I'll give you a very brief story about the axion. So if you look at the stuff that holds nucleons together, it's the stuff that makes the center of the atom hold together, and you look at the force that makes it fall apart, the strong force and the weak force, they behave very differently, or rather, let's see. So we'll start with the strong force, the stuff that holds it together, looks basically the same going forward or backwards in time, and yet the stuff that makes these nuclei fall apart looks very different going forwards and backwards in time. And this ends up being very strange, because if you go and take all your measurements and you write down all the best equations we've got, this means there's two things that are canceling out, not like, just mostly canceling out. They cancel out with 10 zeros, or it's basically, if you divide these two things, you get 1 point and then 10 zeros at least to confirm our measurements, which is very unusual, and so you kind of need an explanation. And the explanation is something called Peccei-Quinn symmetry, which blah, 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 and suddenly you've made a new particle. That's really, the stuff in the middle, it's important and interesting, but not for this point. There's a new particle called the axion, and interestingly enough, is if you have this axion, then in the early universe, you produce a whole lot of this particle and it's still around. That sounds like something we need. So, axion dark matter, we want to find it. Now, how do you find it? Because we know that if dark matter is, if dark matter is in this room and yet we haven't detected it yet, it must be really hard to detect. It couples extremely weakly to electromagnetism. What does that mean? That means that dark matter and light can touch each other only just a little bit. How do you build an experiment to look for something that's only very, very weakly interacting like this? And in the case with axions, I have before me what is mathematically identical to what you write down when you're trying to when you solve this equation. Now, I'd be writing down Maxwell's equations and solving for electromagnetism, but in this case, we're going to do it with sound waves. So on the right-hand side, we have the axion field. It's a tuning fork. And the left-hand side, we have an electromagnetic resonator, which is a big tin can. Well, it's like a copper. You'll see it later, but in this case, it's also represented by a tuning fork. And the extremely weak interaction between dark matter and normal matter is modeled here by the fact that these aren't touching. They're just kind of these two boxes pointing at each other. So let's see if I can set this up. Now, dark matter is always all around us, so I should hit the tuning fork so it's always going. There it's going. So there you go. So we excited energy in our dark matter, and because this tuning fork here was exactly tuned to the frequency of that tuning fork, we could transfer the energy, even though it's just very weak, just through the sound waves between the two. Now, of course, if I do this with the this tuning fork detuned, so I just move that weight, no good. So let us go on. That's it. That's how this works. Good. That's how this works. Right? This is a tuning fork. This is a tuning fork, but it's in electromagnetism. We have to tune it exactly to the frequency the axion is moving back and forth with. We don't know that frequency. Our best minds are trying to predict it. They give us, well, it's bigger than like 100 megahertz, and it's smaller than maybe 100 gigahertz. So, there's a lot of stuff that's covered in there. There's cell phones, there's Wi-Fi, all that. So there's a lot of building that goes on in my lab. This right here is about 800 megahertz, and we're working our way upwards. And so I'm pleased to say this is over at SEMPA at UW here, and we are operating this experiment. And we just started last year operating with the sensitivity needed to find dark matter, but we don't know where it is. So here we are sitting tuning this thing. Tick, 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 tick. It's very slow because you have to listen for it the whole day. But it really is. You're just listening for a tone. And so it may be that this year, next year, the year after, those of you here for CUWiP, this is a great thing to get on graduate school because, just any day you hit the right frequency, bam, you got it. Dark matter, bottle and selling it. Well, maybe not bottle and sell it, but I will tell you a whole lot more about astrophysics and the universe we're made in, or the universe that we're living in. So I'll conclude with, so everything you thought you knew about the universe is actually only a small part of it, sorry. But we're working on that. Thank you.
Okay, let's thank Dr. Rybka again for that awesome introduction to dark matter. Okay, our next contestant is Dr. Emma Schmidgall. Dr. Schmidgall is a world-traveling quantum physicist, having studied physics in California, England, and Israel before ending up at the University of Washington. Her favorite part of her job is the fact that she gets to point lasers at diamonds and play with interesting physics. All right, let's welcome Dr. Schmidgall.
Right, can everybody hear me with the CUWiP mic? Yeah. Awesome. So, I make these. And they're very, very, very cool and very, very, very pretty and very, very hard to make. But let's just take a look at how cool these things are to begin with. So, like any good scientist person, I put a scale bar on the pictures. And whenever you show micrographs, you always put a scale bar. So this scale bar is 5 microns, which is like this gap right here. This one's 10 microns. That's about from here to here. But the thickness of a human hair, that stuff on your head that's really thin, gets everywhere, gets lost, all that, is 100 microns. So these things, these beautiful, beautiful things, are 1/10 of the size of a human hair, which is really, really cool. Okay, so that's really, really cool. What is it good for? How is this in any way related to physics, and why are they quantum building blocks? Well, quantum computers are a very, very popular topic right now. As a matter of fact, we already had one talk on them. And Wired has a guide for quantum computing. It's actually really good. Recommend it. Look it up. The New York Times likes to write about quantum computers. Sometimes it can be a little scary what they write about. The BBC thinks that we're almost there, so good on them. I'm encouraged by their optimism. I think it's great. Even the Prime Minister of Canada is getting in on the act. He went to the University of Waterloo and now can school reporters in how quantum computers work. And they make board books for babies. So they've got quantum entanglement for babies. They've got quantum computing for babies, quantum optics for babies. My kid has the box set. Apparently my household's a little atypical. But in any case, quantum computing is a very, very popular topic right now. And it's popular because if we can manage to build a quantum computer, there are some really cool problems that we'll be able to solve, in some cases, that we just can't solve right now, and in other cases, much faster than we're able to solve right now. So a bunch of people are looking at how do we build these things, and some of them are your favorite 3-letter agencies because big, powerful computers are interesting to people who need big, powerful computers. In any case, quantum computers are based on quantum bits, or qubits. So classical computers are based on bits, and they can be either a 0 or a 1, whereas quantum computers, based on qubits, that qubit can take any value combination of 0 and 1. So people generally represent it as an arrow from the center to some point on the surface of this sphere, and there's an infinite number of points on the surface of that sphere. But that's a little complicated. That picture looks a little technical, and I'm not supposed to do that. So here's a better explanation. Point it at the computer. Whoop. Dang it, I ruined my joke. In any case. So your classical bit can be either, say, a duck or a rabbit. And your qubit, which you've already seen, is this thing, which I look at it and go, it's a duck, it's a rabbit, it's a duck, it's a rabbit, it's in any case. So people all around the world are trying to make qubits, and there's many different systems that people are looking at for how to make qubits. So I put kind of a photo gallery of a whole bunch of different kinds of qubits. The trapped ion ones you heard about earlier are here. I've worked with these guys, I've worked with these guys, and I don't really care what my qubit is for the rest of this talk. So what I care about for the rest of this talk is what happens once you have the qubit. What comes next? So in a classical computer, you have a bit. It gets turned into a whole bunch of electrons, and then you send these electrons through a wire on your chip. They go to other bits, and basically you've got lots and lots of electrons and you know how to connect them together. Now, for many of these qubits, you take your qubit and it emits a single particle of light, a single photon. And here's my, my photon joke. A photon checks into a hotel and is asked if he needs any help with his luggage. No thanks, I am traveling light. So, got a bad physics joke out of this talk, something to go home with. In any case, the important critical part is that your qubit will emit one photon. This could be a little bit problematic. So here's how this could be problematic. Suppose I have 2 qubits, and I want to connect them together. So each qubit is going to emit a photon, and these photons are going to interact. And when they interact, I have connected my qubits. Okay, so far so good. I have my 1 qubit, it emits my 1 photon, and now I have 2 connected qubits, yay. But what happens if one of the photons gets lost? Or, in order for them to interact, they need to be the same color. What happens if my 2 qubits are ever so slightly different and my photons are 2 different colors? So, if I want to connect together lots of qubits, as in enough qubits to actually build a quantum computer, I need lots of same color photons. Many, 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 many same color photons. Because the number of connections I can get is proportional to the number of photons, and in order to be able to connect them, I need to have everything at the same color. So these things that I showed you on the first slide, these really cool, really tiny devices, are actually meant to be kind of like Legos for building a quantum computer. Because these are devices that are supposed to help us get more photons and more photons of the same color. And the hope is that once we get really good at building all of these blocks, we'll basically have a gigantic bucket of Legos, which I guess these days they come as kits for building specific things, but they used to have this old school, like big plastic tub of just random Lego bits. Basically that, where we can connect them all together and build a quantum computer. So I'm going to take you through an example of how we can fix photon color with a device. So suppose I have a qubit and it's feeling a little green and spitting out green photons. Now what I can actually do is I can connect this qubit, apply an electric field to the qubit, and that electric field can actually change the color of the qubit. So instead of emitting green photons, it now emits yellow photons. And so if I can make a device that can fix the color of my qubits and fix the color of the photons that they emit, then I can use this device to help connect qubits together. So I will show you how we make devices, because it's cool. We start with a blank surface. And this, in our case, we use diamond. So this is diamond, and then on top of it's a little bit of semiconductor. And we spin on a liquid called resist. Now, this resist is really cool in that if you shoot a bunch of electrons at it, it turns into glass. And then it protects the material underneath it from everything that comes next. So we can write patterns into this resist, and it's those patterns that turn into our devices. So step number 1, we write our pattern. So in this case, these are the little devices that I'm going to make. And then we want to be able to apply an electric field to our qubits. So our qubits are going to live in these little circles. The light we're going to look at is going to come out of this long wire. And we need to be able to apply an electric field to this. So then we have to add electrodes. So just simple, put down some metal around it. It's easy peasy. Well, never mind. It's really hard, actually. It took me a while to figure this one out. And then we just go into the lab and test this thing. Well, in reality, when you make these things, it looks like this. So this is me. And I'm making devices. As a matter of fact, in the computer in the back, this is like, I was doing a selfie in the lab because this is, you can put it on Facebook and then people like it. But you can actually see devices in progress over here. This is an electron microscope behind me. Basically, really, really, really powerful microscope so that you can actually see these things. And the reason I'm all dressed up is not to protect me from this, but to protect this from me. These things are so tiny that if a hair or something were to fall on them, I could wipe out a whole bunch of devices in one go. So basically, this suit just keeps me from dropping stuff on other devices. Then we take them to the lab and we measure them. So like I said, we attach an electric field around the qubits. We shine a laser on the qubit to excite it, and we look at the light that comes out. It actually looks like this. Do optics because you get the best colors and the best photos. So my lab looks like this. I get shiny things. I shoot lasers at diamond. It's very cool. But really, all it is that simple picture before where I have a voltage that I applied to a thing and I shine a laser at it. So this is what the results of the experiment look like. So over here, again, my little measurement setup, I apply a voltage, I shine a laser on it to excite my qubit, and I look at the photons that my qubit spits out. And what you see here, did the battery on the laser bit just die? It did. Okay. What you see over here is that as I change the voltage, this axis here that says wavelength, that's color. So as I change the voltage, which is on the y-axis, the color is changing, which is exactly what we wanted to see. So my device can fix the color of my qubits, or the voltage is the black squares, the color is the red diamonds, and you can see that the red diamonds follow the black squares. So I'm able to fix the color of my qubits. Will it still flip the slides? Yes. Awesome. Oh, well, I think I'm done pointing at things. Okay, so this is an example of one brick. But if we're going to build a quantum computer, we need many bricks, and then we need the ability to put them all together in something that looks really fancy like this. Or functionally, we need enough Legos to be able to build a computer. So with that, this is the group I work with. I'm a postdoc in Professor Kaimei Fu's lab. I work with a bunch of grad students, and I had to dig up an old group picture to get all of the grad students there. And then also, you have to thank the people who help you out. So it's really important to also have good people at home, and my kid was the model for the thing. So yes, I make Legos. It's cool.
Okay, let's thank Dr. Schmigdal again. Our next contestant is Dr. Sarah Tuttle. Dr. Tuttle is an assistant professor of astronomy at the University of Washington. When not making plots about otters, she is a pretty fair juggler and has never met an audience she hasn't bribed. Oh, that's crossed out. It's supposed to be liked, an audience she hasn't liked. Okay. Let's welcome Sarah Tuttle.
I could also talk about the black screen. I've spent a lot of time in front of blank screens. Okay, so are you ready for galaxies? Yeah. Me too. Unlike Gray, I'm going to talk about stuff we actually, that exists. It's cool. Ooh, I know, right? I hear there's a coffee mug in this, but we might have also been told there was tenure, so now, stakes are changing. We got to be careful here. So I'm going to talk about galaxies. I'm also going to talk a little bit about telescopes, pieces of telescopes, instruments for telescopes that I also build, and a little bit about otters. It looks like the bottom part of the slide is missing, but it means I can just tell you whatever I want is there. So, oh, yeah, that's not great. Okay. Do you want me to just do it that way? Yes. Please hold. We could go through 2/3 at a time. It could get very exciting. So galaxies are important because galaxies are what we see in the universe. And shortly, yes, could be. Okay, perfect. Before I get started, I just want to make sure that we acknowledge the land that we're on. We're occupying land here that is for the Coast Salish people's land, as well as the Duwamish and Muckleshoot tribes. Okay, we'll get pieces of everything. I'll come over here so I can scroll. So what do we have in the universe? First, we're going to start by looking at the universal energy budget. As Gray alluded to, the universal energy budget is spectacular for a few reasons. First, because it only has 3 items in it. This is the tidiest budget you could imagine having. Like, my home budget is more complicated than this. The other thing you might notice is that astronomers and physicists are incredibly lazy namers. Because, come on, dark matter, dark energy, all we're telling you is we totally have no idea what's happening here. In the universal energy budget, what you might notice is the largest part of the pie, almost 70%, is dark energy. Do you know what dark energy is? No. Yeah, us either, but there's a Nobel Prize in it for you if you do. So that's all of this. So Then we have dark matter. Apparently there's tuning forks involved. we discover them using galaxies, so I'm sure you know which my favorite part is already. And that leaves about 5% of our pie for galaxies and otters and really everything else. Now, we can also zoom in a little bit on that part. Hold on. Now, the other thing we can do, you'll be surprised to know this is the most I've ever made pie charts in my whole life. Scientists never make pie charts, but for this it seemed worth it. So we also can zoom in on that 5% and look at the universal baryon budget. So these are particles that we're used to interacting with, and I'll show you what they look like in a minute. But what you might notice is that most of the pieces of the pie here are labeled with things that you are not that familiar with. In fact, they're almost exclusively gas. Hot gas, cold gas, diffuse gas, dense gas, and some that we're not great at counting, but don't judge us. It's only 30%. We're getting better all the time. And then a little bit left for galaxies and other stuff. And otters. You know, we have to make sure that we have a place for the otters. Again, it's not a lot, but like 7%. Okay, so what are baryons? Quick sidebar. Baryons are particles that have 3 quarks. Now, I know you usually run around interrogating the number of quarks that your particles have. Feel free to just walk up to someone on the bus. That's how we do it here in Seattle. How many quarks have you got? These include neutrons, protons, and basically everything else that you're used to experiencing. Probably not mixtapes because many of you are younger than 1,000. So, but for some of us, mixtapes, I know, mixtapes are, do you know, I had to explain them to my children. I don't even know what's happening anymore. So the things you're used to, the important things in life, pride flags, chocolate, the moon, and galaxies are primarily baryons. Okay? So there's some good and bad things about baryons. We know about them, and they trace things, and they don't always trace everything, but we can see them, so that seems important. So we're going to go and see what we can learn with baryons. I will remind you, we needed galaxies to find dark matter, which Gray hasn't found yet. So we've got a little edge here. I'm really excited for when they do, though, because I hear the whole building gets cake, so any day now, any day. Okay. So we know what we're looking for. Perfect. Now, the advantage is even though galaxies are a very tiny fraction of energy in the universe, they are all the heck over the place. We're talking, they're like falling out of space like nobody's business. I mean, not actually, they won't fall on you probably, although Joey might have other things to say about that. So, you know, probably will warn you if the galaxies are coming for you. But this is the Hubble Ultra Deep Field. This is actually an updated Hubble Ultra Deep Field. It's from 2014. It uses multi-wavelength data from Hubble. And what's amazing about this part is that this image, which I always think is spectacular, is a piece of the sky that's about this much. So if you hold your arm out like this is what you would see. You know, if you were the Hubble Space Telescope. So it takes some adjustments, but close enough. There's about 10,000 galaxies here. Almost everything that you see in this frame that makes light, except for a very small number of things, are galaxies. There are billions of stars in each of these galaxies. In fact, the only stars that you can see here, I can pick out about 3. There's one here, here. These are all stars that are local to us and in between us and these distant galaxies. Now, if we zoom in, we're able to actually see features of the galaxies. And in fact, again, zooming in, each of these points are galaxies. Billions of stars in each of these small pieces. So the big things, it's not just because they're bigger. Some of them might be a little bit bigger, but it's mostly because they're closer. As the galaxies get further and further, we're not resolving all of their features here. In this image, the only star that you see is here. Everything else is a galaxy. So even though we're only looking a very small amount of our energy budget, we are seeing billions upon billions upon billions of stars. In fact, we expect that there are planets around almost every one of those stars, right? So the scale of this is just staggering. Now, what I want you to think about is, why do we use galaxies? What are they good for? Now, I use galaxies because I think they're totally fascinating and interesting to know about. But the cool thing is they're a laboratory for us to take physics that we're understanding on Earth and blow it up to scales that we start to push the edges of what's possible. So this is how the discovery around dark matter was made. Because when we start making measurements of things that are larger and larger and larger, we're asking, does physics actually work the way that we have interpreted it? using the things around us like frogs and chocolate, right? What happens when we take it up to the size of billions and billions of things, billions of stars? And the answer is we were missing a big piece of physics. But that's something we can't search for on Earth until we were able to explode the scale, right? So we needed that contrast. We needed to sort of change our perspective. Now, we have to measure these galaxies somehow. So I'm going to share with you a few of the projects that we are working on here at UW that we have built and are building. So this is the Sloan Digital Sky Survey. It takes place at Apache Point in New Mexico, as well as Las Campanas in Chile. And what's cool about Sloan is it's been going on for over 20 years, and it keeps getting rejuvenated. So first we had images of galaxies, then spectra, then multiple spectra. And what's incredible is if you look here, there are fiber optics in these cables. And for every galaxy that gets observed spectroscopically, someone plugs that fiber in. So we actually have someone plugging plates. And these plates, these are giant aluminum plates that get drilled in the basement of the Physics and Astronomy building. You can go visit them. It's super exciting. We actually just gave a whole bunch of them away at the last week's astronomy meeting. And I want to show you a few of the exciting results. So these are images from the Sloan telescope. These are two galaxies. And what you can see here is that they're boring, galaxies. If galaxies were boring, but these galaxies are a little bit plain, and we're studying them because they're unusual in that their disks are very red, so they're not forming stars. Usually, spiral galaxies like the Milky Way form stars. And we're trying to find out why that is. And the one I want to draw your attention to is up here with this funny pink that I've zoomed in on. It turns out that this galaxy is probably not forming stars, because it's actually the remnants of a merger. So we know that sometimes galaxies crash into each other and make bigger galaxies. But because it takes so long, they can be hard to find. This one is making hot gas because it's having shocks crash together, and that stops stars from forming. So we're able to do that in my lab here. Definitely my lab. Definitely, in PAB. We're able to build instruments that allow us to do that. So these are two instruments called integral field spectrographs. And when we replicate the integral field spectrographs, we're not only able, now watch this, I'm going to jump right over gray. We're not only able to study galaxies, we're able to use galaxies to study dark energy. So we study Lyman alpha emitting galaxies to constrain dark energy. And so we have new data coming in on this now. I built an outrageous number of spectrographs that we will not speak of without drinking. And we're able to measure with these instruments all different characteristics of stars and galaxies. We have kinematics, stellar ages. Here we even have extended gas emission. So I just want to pitch very briefly, we're building in our basement a new experiment for Sloan, and we're going rogue. You'll be surprised to hear. We're actually building robots. Robots are taking over from the plate pluggers, and we're going to use robots to study galaxies. So this is not filled with $1 million, although that might be a cooler prize. We are building fiber optic robots. Ooh. I know, they're so tiny, right? Oh well, next time you can come visit them when you're done. But we're building robots that will allow us to study these galaxies, millions and millions of them, both nearby and all the way out to the edge where we'll study the formation of supermassive black holes. So if you have questions about fibers, my inability to click on things, galaxies, or otters, I look forward to talking to you very shortly. Thank you.
Okay, let's thank all 5 of our contestants again, and especially Sarah Tuttle's ability to persevere through technical difficulties. All right, now we have a few minutes to hear from you. So I'm sure you've thought of lots of questions you've wanted to ask of all of these amazing physicists. So now's your chance. So if you'd like to ask a question, we are setting up a microphone on either side. So please line up and get ready with your questions. Also, please get ready to vote at the URL that we will share shortly. Excellent. So the URL up at the top is where you can vote. Beneath that is the Wi-Fi information, which may be important to be able to vote.
So you're just going to hand this back and forth.
What's happening? Oh, sorry, yes, what am I doing? Are there questions?
There will be questions. Yeah, so you can just hand it.
Okay. Is someone going to supervise this, or are we just totally rogue?
Oh, we'll supervise it.
Okay. Okay. Ooh. It's getting serious in here.
Okay, so first question for you.
This is for Megan Ivory. Okay, this question is for Megan Ivory. So you mentioned that barium-138 ions, I believe, are used to create these qubits. But why the barium-138? What properties does it have that makes it good for this?
There are a lot of ions, actually, that people are using to study quantum information. Barium's just one of them, but because we do most of the addressing with lasers, one of the most important things that we have to consider is, can you buy a laser that happens to be the color that is the ion's favorite color? And there are a lot of ions out there that have favorite colors that are in the UV spectrum, which are very difficult to get lasers for, and a lot of others that are way up in the infrared spectrum. Barium happens to have wavelengths that are readily available in lasers today.
Great, thank you.
Thank you.
Okay, is this on? Oh, yeah, it is. Okay. Hi, so I'm Quinton Conine. I'm a senior at the U of O. And something that I've always wondered about qubits is, so in regular bits, one of the big benefits of them is that you can have all sorts of analog circuits, but with binary bits, you're able to get some redundancy there so that you have less errors. So with a qubit, where you don't just have that on and off sort of behavior, how do you keep error correction?
You use more qubits, actually. So there's all sorts of schemes for how you do error correction with qubits, and pretty much all of them have extra qubits. So physically, you'll have 5 qubits, but it'll act as 1 qubit. So like when you need to actually figure out what the value of that qubit is, you go ask all 5 of them, okay, what are you, what are you, what are you, what are you, what are you? Okay, we are 7. So things like, basically that's how you build in the error correction.
Thank you.
I'm Matt. I don't actually go to school anymore. I actually want to, this one's for Emma. I'm trying to figure out, so when you do actually have flipping between bits, 0 to 1 in these qubits, how do you actually target which one you want to use? Because you have to know which one is going to be the 0 or 1, right? How do you actually target them with your lasers?
So at the moment, when we build these things, we put in basically a whole bunch of the defect in diamond that we use as our qubit. We put a ton of it in. And then when we build those disks, each disk will have 2 or 3 at the edge of the disk. And so then we just pick one and say, okay, let's look at this one and see if it works. And then we go through and try several of these devices. So you're right, though. In the future, when I actually build a big computer, I'm going to need to know, okay, in this, these 4 disks, I have qubits that work, and then over here I've got another 3 disks with qubits that work, and then I've got some sort of switch that'll connect them together. So yeah, that's another tool that another block that I'll need to put in my Lego kit.
Okay, TBD.
Basically, TBD.
Thanks, Emma.
Right, over here.
So I have a question for Gray Ribka. So how do we know the purpose for dark matter if we can't detect it with any of our senses and we can only know of its presence with specific frequencies?
So we know about it from the motion of stars and galaxies about each other. It's probably a better question for you, actually. I'm looking for it in the lab, and that's the stuff we can't do yet. Here, let Sarah talk about how we know about it.
Oh, sorry, was this a question about real things? I got you.
Yeah.
Okay. He can take it. He's got you. So with dark matter, so dark energy, we definitely know nothing about. we'll just leave that in a corner. Dark matter is pretty cool because, as Gray mentioned, we need it to explain many different kinds of observations. So one of the observations we had is this idea that when galaxies are spinning, we should be able to predict, as you go further and further out, how fast the stars are moving. That has to do with the mass of the galaxy. Almost every galaxy that we measure, the visible matter, it's just not enough. Now, interestingly, there actually was a paper that came out just this week, and there's been some back and forth, but there's a galaxy we might have found without dark matter. So it used to be that we thought dark matter was wild, but now we might have detected it through its absence, which is weird. We also can see it get left behind. So when you take big things and merge them, like galaxies or clusters of galaxies, we can measure those galaxies in different ways. We might count the stars, we might look at the hot gas, but we can also measure the gravity that gets exerted on everything around it. When we look at the gravity, we're missing mass again. So we have different ways, different systems that we're able to look at, and when we try to count up the mass the way that we usually understand gravity to work, we just can't find enough stuff. And we've tried different solutions. So one of the cool things about physics, which is probably not how it works, but is still a possibility, is that actually we're getting our physics wrong. It's not that we're missing particles. We could be getting our physics wrong. So maybe there's a different solution. So there are still people looking for other solutions, not just particles. Although in general, the physics community has come around. So we make lots of different measurements of objects in space. And then eventually we have to turn to theorists and particle physicists and we say, look, we can't find anything that works with everything we know now. We need some new explanations. So then we end up with big labs tuning things up and down because we just don't have enough constraints.
From this side now.
I have a question for Joy Key. So during your talk, it sounded like the gravity waves hit Earth before the light waves did. Does that mean gravity waves would be faster than the speed of light?
Excellent question. As far as we can measure, gravitational waves travel at the speed of light. You're right with the neutron-star merger. The gravitational waves from their in-spiral hit the Earth before the gamma ray burst. That's because the gamma rays were created after the merger, but they were all traveling at the speed of light through the universe towards us to hit us.
Thank you.
Hey there. Thanks a lot, first of all. Second of all, some of us have kids here that are sort of pre-college age, and I thought maybe a couple of you could tell us what you thought. You know, if you're interested in hard sciences, maybe you're interested in physics, you're a high school kid or a middle school kid, what would you recommend those kids do? No one wants to answer. That's fine.
Take lots of science and math classes, but do stuff find stuff you're interested in. That's the real answer. Do stuff that you like to do. There's lots of work to be done, and we need lots of people to do that work. And so figure out what you like to do and learn as much as you can about it, and you'll really get to explore once you're in college. So find something you're interested in.
You do not want this? No. I will also say, and this is not advice parents want to hear, but I have an 11-year-old, so I feel totally legit and ruining everyone's life here. Yeah, go outside in the world. Because actually, I think the things that I have benefited from the most, I've had lots of wonderful classes and wonderful mentors and research experience. But a lot of things when you're working on kind of the cutting edge of physics is incorporating a lot of other experiences you might have had when there's not directions for how to solve problems. One of kind of the biggest moments when you start doing research is that moment when you go to ask someone how to do something and everyone's like, I don't know. I guess you have to go figure it out. And you're like, oh, yeah, I cannot Google this. I am going to have to work it out. And so I think the more experience you have kind of doing different things that you find interesting, not even necessarily inside the classroom, allows you to have a deeper experience there. Right? So you carry all of that with you when you start to come into the classroom, and I think that, or into the lab. And I think that that's one of the things Kaimei was talking about was, you know, the more of us that have all sorts of experiences in the world, bringing it to physics, we come up with interesting solutions, right? We don't know a lot about how the universe works, and so we want your brains that are all filled up with wild and crazy things to come and take some stabs at things, right? That's how we end up with quantum computers. That's how we find gravitational waves, which frankly, people thought of as like a joke for a really long time, right? Like now it's like, oh, cool, multi-messenger astronomy, like that's what you should write your postdoc application about. Like 20 years ago, people were like, why are you wasting your time? That's impossible and not happening, right? Like someone said they did it and everyone just wrote it off. So there's a lot of really powerful stuff out there that comes from your imagination and experience.
I just want to add something for the shy people in the room, because I tend to actually be shy. Don't be afraid to ask questions, because there was a lot of time when I was studying physics in high school and in college, and even a lot in graduate school, in fact, where I was worried that I was supposed to already understand something, and so maybe I shouldn't ask the question, because then I'll be the person who doesn't know. But in fact, you won't learn that way, and oftentimes when I talked about those questions after the fact, I found that my classmates didn't know them either. So I just want to encourage everybody to always ask lots of questions and never feel shy about doing that.
Okay, we have time for one or two more questions.
I have a question for Gray. So I was thinking, what are the chances to find the right frequency? And since you mentioned there's a very large range of frequencies, so how do you narrow down the range, and how do you target the certain frequency to test for?
Okay, that's a really big question. Yeah, I tried to stay away from the plots that have the predictions. And it's because the question of how long till we find it with our current experimental program is actually, it's a theological question, because it involves, so you're imagining some creation myth, and there is something, and it's throwing darts at the frequency scale. And this is kind of a physicist joke, apologies. And it really matters whether it's on a linear or a log scale axis. So I can say that over the next 5 years, we are covering a significant fraction of the kind of best, most favored range. And so the odds are good, but it's very, very hard for me to put a number on it. Where does that range come from? The range comes from, the range comes from, so you take everything you know about physics and cosmology, and you plug in a particular frequency, which corresponds to a particular mass of a dark matter particle, and you say, does this give me the right amount of dark matter that I see in measurements today? And if it does, then you say, okay, that's a good one, you should look there. And if it does not, then you say, that's probably wrong. The problem is that there's a great deal of uncertainty on that, and that's why you get a huge error bars, because it kind of requires you getting everything right since the beginning of time to now in all of your physics, which is... We're better than you think. Which is
things to work out.
Yeah, which is I think they have a very low bar, so.
Okay, we have time for one more question.
How did you capture the sound of the black holes colliding if there aren't a lot of good ways for sound to travel through space?
Very good question. That is right. The way that our ears work when we hear sound is from air vibrating, and there is no air in space, so sound doesn't travel in space. But the LIGO detectors, the data, we can actually, so there you saw those sort of wiggles when we heard the sound. You can actually make speakers vibrate with those same wiggles. So we can put those waveforms or those wiggles onto speakers and shake the speakers, and our ears can hear that. So that's right. If you were out in space, you would not hear the gravitational waves, but but LIGO can hear the gravitational waves. They are like our ears.
Thank you to our slammers. Okay, so the votes are coming in. You have exactly 1 more minute to get your votes in. We're going to start playing Jeopardy music with 30 seconds to go.
Quick vote. Yeah, I know. We're allowed to vote, right? I think so, yeah. Like if you run for president, you get to vote for yourself.
Joey, have you ever heard of a guy named Thomas Kalanick?
Do you know where he is?
Colgate. Oh, okay, I just wondered. I went to high school with him, and he's doing a similar kind of research in astrophysics.
Yeah, I mean, it's sort of small circles, so there's sometimes a chance, but I don't think so.
Yeah, that's why I thought it might be a smaller circle. That I know he's been out here and used the telescopes out here at times.
Okay, the results are in. We have a winner. We have a lot of winners. In fact, we think that you are all winners, so you all get a CUWiP swag bag, which includes CUWiP socks.
Okay, and now, the moment you've all been waiting for, the winner of the inaugural UW 2019 Physics Slam. And the winner is Megan Ivory. For all your caffeination needs. But wait, there's more. You may not have won second place winner, but we think you have potential. Sarah Tuttle. All right, awesome. Let's thank our amazing slammers one more time. And thank you, everyone, for coming. We hope you have a wonderful night. CUWiP attendees, please stay seated.